In section 5.2, we're going to talk about what's called the characteristic equation, which is what we use to find eigenvalues, and then we'll look at a couple applications of eigenvalues and eigenvectors, which really are pervasive not just throughout mathematics, but lots of other disciplines and topics and applications. They really do come up quite a bit throughout just applications in general. And so we had started this page at the end of the last section, and I'll just sort of review what it says. So we're trying to find eigenvalues, right? And so this is the relationship between a matrix A and its eigenvalues and eigenvectors. So AX equals lambda X. Again, A is a matrix, X is the eigenvector, lambda is the eigenvalue. And so we want to solve this equation, and so we subtract everything over to one side. We factor out the X. When we factor out the X, we have to include this identity matrix because we have a matrix minus a matrix here, so we need that to be defined. And then we want to solve this homogeneous equation, right? This is A minus lambda I as a matrix times X, which is a vector, equals the 0 vector. Now, we want this to have a non-zero solution, right? So we want X to be not 0. And so that's if A minus lambda I, which is a matrix, again, if that's invertible, this is going to end up being the trivial solution, right? X equals 0. And so since we want it to not be 0, we want A minus lambda I to not be invertible. And so what that means, there's a lot of different ways to think about that. That means we want it to A minus lambda I to have a free variable, or the other way to say that is we want the determinant to be 0. Thus, that means if we want a non-zero eigenvector, we do the determinant minus of A minus lambda I, and we set that equal to 0. And this is what's called the characteristic equation, which is exactly what it says right here. So a scalar lambda is an eigenvalue of a matrix if and only if lambda satisfies the characteristic equation, determinant of A minus lambda I equals 0. And so that's how we find eigenvalues. And that's what's sort of summarized right at the bottom of this page here. It says if we want to find an eigenvalue, you write down the matrix A minus lambda I, you do the determinant of that matrix, which is going to give you the characteristic equation, and then you set that equation equal to 0 and solve. And then to find the corresponding eigenvector, you plug lambda back into A minus lambda I, and then you solve the homogeneous equation A minus lambda I x equals 0 for x. And there will be a free variable for that's involved in that because otherwise we'll get the trivial solution. Okay, and so that's what we're going to do in the next couple pages. We'll look at a couple examples. I'm hoping that you'll try it an example or two, and then we'll look at an application that'll let us try an example or two. So let's find the characteristic polynomial and the eigenspace of this following matrix. This is a 3x3, and so 3x3s definitely require a little bit more work because you have to do the determinant of a 3x3, and if you remember, the determinant of a 3x3 is a little bit more involved, but it's okay, we can do this. And we're going to find the eigenvalues and the eigenvectors. So just to be clear, when you see the word eigenspace, that means find the eigenvalues and their corresponding eigenvectors. So here's our matrix. This is A. On the last page, we just said we need to do A minus lambda I and then do the determinant of that. And so let's write down A minus lambda I. Well, lambda I is lambda on the diagonal of the identity matrix. And so when you do A minus lambda I, it just takes lambda and subtracts it off the diagonal entries. And so A minus lambda I looks like this. It's just A with lambda subtracted off the diagonals. So that's A minus lambda I. Again, we want to do the determinant of this matrix equal to 0. So when we do the determinant of a 3x3, we want to expand across a row or a column that has a lot of zeros, right? So we would want to use either the first column or the first row of this one because there's 2 zeros in both. I'm just going to choose the first row, but either one would be good. And remember, that's just going to reduce the amount of work we have to do. And so let's expand across the first row, right? We pull each of these entries out. We alternate signs as we do. And then we multiply by the determinant of the submatrix that we get when we delete the column and the row of that entry. So it looks like this, right? So the determinant of A minus lambda I, this is the determinant of this matrix. So we pull out the first entry, so 3 minus lambda, and it's got a plus sign with it. and then we're going to multiply it by the determinant of the submatrix we get when we delete that row in that column. And so we're going to multiply by the determinant of the submatrix, that little 2 by 2 right there, the minus 2 minus lambda, 4, 1, 1 minus lambda. And so that ends up being AD minus BC, which is this. AD minus BC. And then when we pull the other entries out, they're just 0, right? And so you're going to end up multiplying by 0, so I'm not even going to write them down. And so this is the entire characteristic equation that we can simplify and set it equal to 0. And so I'm just going to like distribute these two parentheses in here and just kind of simplify this inner part, and this ends up being 3 minus lambda times lambda squared plus lambda minus 6. And we want to solve this equal to 0, and so we're going to set it equal to 0 and solve. Now, you might be tempted to sort of keep distributing here, but don't distribute. Instead, what we can do is we should factor this part, and then we'll be right at the solutions, right? So we want the roots of this thing, and so let's go ahead and factor that part. And after we factor, we get 3 minus lambda, and then this minus 6 factors into plus 3 minus 2. And that was nice because there are the roots, right? We set each one of those equal to 0 separately, and we would get lambda equals 3 minus 3 and 2. And so these are the eigenvalues. For the matrix A. And there are 3 of them because A is a 3 by 3 matrix. So an n by n matrix has at most n distinct eigenvalues. Sometimes there's a repeated one. We won't really get into that in this class, but anyway, there's 3 because it's 3 by 3. And so now if we want to find the eigenvectors, that's what it says right here, we plug lambda back into A minus lambda I. So again, that just means subtracting lambda from the diagonal entries. And then we solve the homogeneous equation. And so let's do that. So I'm going to find the eigenvectors next. And we'll go through them one at a time. So let's start with lambda equals 3. When we plug in lambda equals 3 and we do A minus lambda I, again, you just take the matrix A and subtract lambda from the diagonals. And so that's going to be this. 0, 0, 0, 0, minus 5, 4, 0, 1, minus 2. Right, that's A minus lambda I. And we want to solve this equal to 0. Right? And so we want to solve A minus lambda I x equals 0, and the x will be the eigenvector. And so let's take this matrix and put it in there with a column of zeros. So this is just solving the homogeneous system, which we saw in an early chapter in chapter 1, an early section in chapter 1, I mean. And when we do this, this is the row reduced version. Right, so if I do RREF, oh, I'm sorry, that's not RREF. I just wrote down the matrix. Sorry about that. So I just set it equal to 0, and right away I thought it was RREF because I could already see that x1 was a free variable, right? And so I can see x1 is a free variable, and so I know x1 equals x1, and then we can solve one of the others here to realize that we get v1 or v2 equals v3 equals 0. Oops, I mean it's x, excuse me. x2 is 0 and x3 is also 0 when we go ahead and we solve this matrix. And so this has the solution 1, 0, 0 times x1. And so that means lambda equals 3 as eigenvector 1, 0, 0. So that's the eigenvalue eigenvector pair. And you just do that for each different eigenvalue. So I'll just keep doing it in a similar fashion here. So I picked out lambda equals 3 first. Let's do it with negative 3. So I'm going to subtract negative 3 from the diagonal entries, which is the same as adding 3. Right? And so let's do that with lambda equals negative 3. So when I subtract a minus lambda I, or let's actually just cut right to the chase. We want to solve a minus lambda I equal to 0, right? And so we're going to add 3 to the diagonals and then set it equal to 0 and row reduce. And so this looks like this. 6, 0, 0. So this is a with 3 added to the diagonal. We want that to equal 0. This is my a minus lambda I, and we want it to equal the 0 matrix. Let me go ahead and maybe just show you the row reduced version, right? So these two rows are the same, and so they would cancel each other out. And so let's just do RREF and see that we would get this matrix. I guess this is just technically REF, since I didn't put 1s there. But anyway, we can still solve it, because we see now x3 is a free variable, x1 is going to be 0, and x2 is going to be written in terms of x3. Right? So from this, we can see that x1 equals 0. From this second row, we see x2 equals minus 4x3, and x3 is a free variable. And so we get this the vector 0, minus 4, 1 for this one. And so lambda equals negative 3 as the eigenvector 0, minus 4, 1. And finally, we do the same thing with the last eigenvalue, lambda equals 2. So we'll subtract 2 from the diagonals and solve the homogeneous equation. So let's do that right here. So for lambda equals 2, we'll solve a minus lambda I x equals 0. So again, subtract lambda off the diagonal, solve the homogeneous equation. So when you subtract 2 off the diagonal, you get this. Double check and make sure that this makes sense. You're not just copying down this matrix, but take a second and see that, hey, oh yeah, we did subtract 2 off the diagonal entries. We set it equal to 0. And again, if we row reduced, those two rows could be multiples of each other if we multiplied by 4. So it could just be something like this. Again, v3 is free. v1 ends up being 0, x1, and so we get x1 is 0, x2 equals x3, x3 is free. And so we get 0, 1, 1 as our final eigenvector. So lambda equals 2 as the eigenvector, 0, 1, 1. And so just to be clear, you can always double check that these are correct, because in all cases, what we should find is ax equals lambda x. So you can always double check that when you take your matrix and you multiply it by the eigenvector, you get the eigenvalue times eigenvector. That just can, if you're ever second guessing yourself or on a test or something and you want to just do a quick check, that's how you could double check you're correct. Okay. So this is a 3x3. We won't do ones that are bigger than 3x3. Typically in classes where you're not using a calculator to do this stuff or a computer, you stick with 3x3s as the biggest because this is complicated enough. You get a cubic, right, which is hard enough to solve. Once you had if you had a quartic, like a degree 4 or higher polynomial here, it becomes very challenging to actually solve. And so most of the times we stick to no bigger than 3x3. And really, usually what we do in tests and things like that is we do 2x2s. Since those are much easier to deal with, you end up with quadratic equations, with which we can use a quadratic formula to solve. And so 2x2s are much more manageable and reasonable to do, I think. And so I did the 3x3 first to show you one by hand, but then usually I have students try this one themselves in class. And so I would ask that you give this one a go and see if you can do it yourself. There'll be 2 eigenvalues and 2 eigenvectors, and you find them in the same way we just found the one a second ago. I'm going to do this one myself, obviously, here. And if you want to see me set it up first, that'd be fine. But again, I really think you should try to do this and then see if you get the correct answer. And if you do, that means you know how to do this. It's great. And if not, that should generate some questions that you can ask to clarify your understanding. Okay, so we're going to do the same thing. We're going to find the eigenspace, except it's a 2x2. And so when we do A minus lambda I, again, you just take the matrix A, subtract lambda off the diagonals, and so that looks like this. Just lambda subtracted off the diagonals. And then the determinant of a 2x2 is also very easy, right? You just do AD minus BC. And so when we do the determinant of A minus lambda I in this case, you multiply those diagonals and then you subtract multiplying those. And so you get 1 minus lambda times 4 minus lambda minus 2 times 2. And you want that to equal 0. So this is the characteristic equation, just to be clear. That's what we call the characteristic equation, and we want to solve the characteristic equation equal to 0, right? We want this matrix to not be invertible, which is why we're solving that, so that we get non-zero solutions. Okay, and so again, this just becomes a quadratic, right? And so we can either factor it or potentially use the quadratic formula or whatever ends up happening after we start to solve that. And so let's go ahead and set that equal to 0 and see what happens. So I'm going to multiply this out and start simplifying down. So when I multiply that out, we get lambda squared minus 5 lambda plus 4, and then minus 2 times 2, so you get minus 4. We want that to be 0. And so the 4's cancel. And so we just have lambda squared minus 5 lambda equals 0. And so this is easy enough to solve without the quadratic formula, right? We can just factor out a lambda to get this, and then we can just see that lambda is 0 and 5. And so these are our eigenvalues. Again, that's a 2x2, and so we got 2 of them, right? You usually get n for n by n's, or no more than n, technically. And then to find the eigenvectors, we just do what's on the bottom of the second page. You plug lambda back in, subtract it off the diagonals, and then solve the homogeneous equation, which again is easier to do because we've got a 2x2. So for the eigenvectors, let's first plug in 0. And so we're going to subtract 0 off the diagonal, and so we're just going to look at the regular matrix. So let's solve A minus lambda I x equals 0. And so that looks like this. That's A minus lambda x, and we're setting it equal to 0. We do our REF, and we get this. Very easy to solve. x2 is a free variable. X2 is minus 2x1, or x2, excuse me. And so we see this, right? x2, oops, let's do this, x1 equals minus 2x2. x2 is free, and so then this solution is minus 2, 1. And so that means lambda equals 0 as eigenvector minus 2, 1. It's interesting, lambda equals 0, so that means that ax equals 0, because lambda x is going to be 0. And so that means this vector is also in the null space of the A. Kind of an interesting thing there. also means that this matrix is not invertible, right? So just things are rushing through my head. That's why I paused a minute ago. Because when 0 is an eigenvector or an eigenvalue, that's part of the invertible matrix theorem, which means that A is not invertible. And we can also see that because the determinant of A is 0. So just connecting things to some past sections, some past things we've learned recently. So that's the eigenvector for lambda equals 0. Let's do lambda equals 5. And so again, we subtract 5 off the diagonals. When we want to solve a minus lambda I x equals 0, and so that looks like this. Minus 4 to negative 1, so I subtracted 5 off the diagonals, right? Looks like that. We reduce it to get our solution. So this becomes 1 minus 1/2, 0, 0. And that's a nice easy solution to figure out. We get x1 equals 1/2 x2. x2 is free. And so lambda equals 5 is eigenvector 1/2, 1. Now, to make this sort of easier to work with, because this one has a fraction, a key thing you should know is that any multiple of an eigenvector is also an eigenvector. And so you could multiply this one by 2 to get rid of the fraction, for example. So let me make that note. So note, any multiple of an eigenvector is an eigenvector. And so 2 times 1/2, 1, which is 1, 2, works as well. So that's just, again, it's just nice because you can get rid of the fractions. Also, sometimes you want to take an eigenvector and scale it so that the values sum to 1. And so that's how you could also do that. You would just divide by something in that case. And so in other words, this still works because, in other words, ax equals lambda x in this case, right? So let's take this one and just show you that works. Let's multiply a, 1, 2, 2, 4, times this new x, 1, 2, and it should be the same thing as lambda times x, which in this case is 5, times that eigenvector. Right, so this is just showing you ax equals lambda x, which is the definition of an eigenvalue eigenvector, and you can see that that's going to work, right? When you do this one, you'll have 1 plus 4 is 5 in the first entry, and you have a 5 in the first entry. And the second entry should be a 10, right? 5 times 2, and you get 2 plus 8, which is 10. So that also worked, just kind of showing you how you can scale in an eigenvector to obtain another eigenvector. It's very useful sometimes. And so I'd like to finish this chapter by just showing a couple applications, maybe just talking about one and then getting our hands dirty with another. And so one huge application that we all deal with all the time in basically our everyday life is Google. And so Google has made millions or billions of dollars off their services of their internet searching. And I know it's more than just an internet search now, but that's how it started, and that's what it's most known for. And the way that Google ranks websites is by using eigenvalues and eigenvectors. And so basically what it does is it very, very quickly, there's more information here if you want to read more about it. It's a fairly complicated thing you can imagine. But in short, it represents the entire internet as a matrix, and the rows and the columns represent different websites. And if a website links to another website, there's an entry in their corresponding row and column. So like if row 1 and row 2 have a 1 in that entry, that's indicating that website 1 and website 2 are somehow linked to each other. Like there's a link from one to the other. And so if you search something, it takes a matrix and it looks for links based on certain phrases that you searched. and then it looks for the eigenvalue and the eigenvectors of this giant matrix, and it turns out the eigenvalues tell it how to rank the certain pages, the web pages that you search for, and the eigenvalues might tell some other, I don't remember exactly what it tells you, but it tells you something about the relative strength of or connectivity between those matrices, or excuse me, those websites. But it's really just a giant matrix operation where they're doing eigenvalues, eigenvectors. We had someone here a couple of years ago at a seminar talk about just that, and it's a very common thing. If you Googled that, I'm sure someone would be doing a video talking about how that works. Again, it's pretty high level though, and so it's a little beyond the scope of this class. Something we can get our hands dirty with is the application that's on the next page. And so this is going to be eventually going to be an application in population modeling. And I have personal experience using these types of population models, modeling turtles. And so we're going to look at this. You can obviously see it's a matrix. And then it turns out when you find eigenvalues and eigenvectors of this matrix, it tells you how the population is growing and how the population is distributed. But before we get there, I want to sort of set it up with a more basic example so that when we get to the a little more complicated example, it seems a little bit more familiar. And so this is this falls into the category of what's called discrete population modeling. And so most of the functions you're familiar with are probably continuous, and discrete means it's like the opposite of continuous. And so let me just maybe write that down. So it's the opposite of what continuous means. And if you remember that definition from calculus, continuous means that all the limits exist at all the points. Or, you know, the physical way to think about that is when you trace your finger along the graph, you don't have to pick your finger up, right? So if we had like a continuous graph, it would look something like this, for example, right? It's continuous because I can trace my pen or my finger along the curve, and I don't have to pick it up at any of those points. But discrete means is it happens in time steps. And so rather than having, if this is time on the x-axis, rather than having all the time steps defined, discrete usually has the integers like 0, 1, 2, etc. And so this same graph as a discrete graph might look more like this. It might take the same shape, but it only exists at discrete time steps. This would be like stepping along in space, the same kind of shape, but it takes discrete steps. So that's what we're kind of thinking about here. And again, we're going to warm up with this bacteria example, and then we'll move on to the more complicated, slightly more advanced matrix model example. So let's say we're modeling a bacteria that starts with 6 bacteria, and it doubles every single time step, whatever that time step is. Maybe it's a day, maybe it's an hour. Different bacteria will populate at different times. And so let's make a model for this. Let's let P sub t be the population of the bacteria at time t. And so we're being told that it starts with 6 individuals. So that means at the 0 time step, so P0, there are 6 bacteria. That's what's being told to us in the problem. And we're also being told that it doubles every time step. And so when we move on to time step 1, P1, this 6 should have doubled, right? And so it should be twice what we started with, which is 2 times 6, which is 12, right? And let's make a pattern here and do a couple more of these and see if we can find a pattern. So that's P0, P1 doubled P0, which got here. If we wanted the next time step, which would be P2, we double what was there in P1, right? Which is going to be 2 times 12, which is 24, of course. But let's think about another way to write this. Instead of doing 2 times P1, we had this expression for P1, right? P1 was 2 times P0. And so another way to write this would be that 2 times P1 could be 2 times 2 times P0, which is 2 squared times P0. I'm trying to come up with a pattern here. Let's look at P3 and P4 and see if we can come up with a pattern. So P3, the population at the third time step, should be twice what we had at the second time step. And this is the formula for the second time step. Right, this formula right here, 2 squared times P0, is P2. And so we could write this as 2 times 2 squared P0, which is 2 cubed P0. Notice the difference between what's going on here. If you step along P1, P2, P3, P4, etc., and you just keep doubling the one before it, that's a fine way of doing this. But if you wanted to figure out 100 time steps down the line, you'd have to multiply things. You'd have to double the thing 100 times, right? You'd have to keep doing it 100 times until you got to that point. What I'm trying to do is come up with a closed form solution that will work for any t you want to use. And so this is a little bit more valuable to look at because this only involves the 0 time step, where this one here, you needed the second time step to get. So I think with one more time step, we should be able to see what's going on here. So the fourth time step, P4, that's going to be twice P3. And P3 is given by this expression right here, 2 cubed P0. And so this is 2 times 2 cubed P0, which is 2 to the 4th P0. Do you see the pattern yet? Notice what happened here. When we wanted the second time step, we did 2 squared P0. When we wanted the third time step, we did 2 cubed times P0. When we wanted the fourth time step, we did 2 to the 4th times P0. And so, based on this work here, can you come up with the formula for the nth time step? If there was an n here, then there would also be an n right here. And so Pn is 2 to the n P0. This is what's called a closed form solution rather than the recurrence relationship. When you just multiply the 2 times the one you had before, that's called recurrence relationship because you need the one before it in order to get to the next one. This expression here does not require the one before it, right? And so if you wanted, in other words, you wanted P100, you don't need P99. You just raise 2 to the 100th power, and then you multiply it by that original P0 which we had. So it's a much more powerful expression because you don't need the ones before it to get any value. Okay, let's generalize this thing. So this is also, this 2 came from the fact that the population doubled every time step. That's why we ended up with a 2 there. And so in general, p to the n is going to be r to the n P0 in general, where r is the growth rate. And so if that r ends up being bigger than 1, it's going to grow. The population will grow. And if it's a fraction, it's going to decline. And so if r is bigger than 1, then the population is going to go towards infinity. It's going to grow. If r is a fraction, then when you raise a fraction to a power, it gets smaller. And so then the population is going to go to 0. It's going to decline. What happens if r is 1? If the growth rate is just 1? Okay, so this instead of a 2 is 1 to the n, then 1 to the n is just 1, and so you just get Pn equals P0. So in other words, all time steps stay the same. And so if r equals 1, then Pn is constant. So this is getting at the idea of this recurrence relationship, these discrete time steps where we have this recurrence relationship that we're then able to get this closed form solution. And so we're going to see a similar thing in the next application of population growth with matrices. And so keep this sort of relationship in mind as we get to the next step. Okay, so this next part is called Leslie population models. As I mentioned, I have a pretty significant experience with this particular topic. It's a very common way to model populations in the wild, in nature, and as many of you know, I do that in my own research. I think about population modeling and disease spread and things like that, and this is a very classic formulation. I just recently finished a project with a Fitchburg State student where we modeled diamondback terrapins using this very type of model. So you can check my website if you're interested in seeing that specific application. And so the sort of the key thing about these Leslie matrix models is they're useful for population that have more than one age class. And we usually want to have more than one age class because we're considering both births and deaths. And so, for example, if you think about like babies versus teenagers versus adults, each one of those classes give birth at a different rate, and they also die at a different rate. And so we break them up into classes to capture those differences. And the way we do it is we represent P sub t is going to be the population, just like we did a second ago, except now it's a column vector. So instead of it just being like the number of bacteria, like the last example, P sub t is a vector, and it has the age classes, the population in each age class in each entry. So depending on how many age classes we have, that'll tell us how big the matrix is and how big P is as well. We're still going to take discrete time steps. And so each sub-entry, like I said, tells you the number of the population in each age class. And then this is the relationship we use to project the population forward. It's very similar to what we just did with the bacteria, right? The population at the next time step, t plus 1, equals the matrix A, which is shown right here, times the population at the last time step. And so this matrix A is really important because it contains all the birth rates and the death rates of the population. So it tells us how the population grows and declines. And then we apply it to the population and it projects the population forward. Okay, so first we've got the age classes spread across the column. See how we've got like 1, 2, 3 to n? And so we have n age classes. And so the age classes are spread across the columns. To be more clear, we have like the P1, P2, P3, to Pn. So the age classes are spread across the columns. In the first row, we have these Fs, and you can see they're defined down here. F is the average number of female offsprings born to each female age class per time step. And so, in other words, these are the birth rates in the first row for each age class. Notice how it's only mentioning female offsprings and females in the population. This is a very common thing in population modeling where you kind of ignore the males in a population, you just model the females. And the reason for that is because females really control the birth, the increase in the population, right? So new births come from females, and oftentimes in many animal populations, that's all that really matters. And really, in animal populations, many times there's like one male that might be sort of controlling the growth and decline of the population by impregnating all the females in the population. So I always think of like hippos. When you look at a huge river of hippos and there's like 100 hippos in one location, they're usually all females, and then there's like one big male that is sort of quote unquote in charge of the whole herd. And then that male is called the bull and sort of dominates and might get overthrown by some other male. But the point is, it doesn't matter how many males there are in terms of growing the population. What matters is the females. And as long as you have one male to sort of impregnate the females, that's usually all that's mattered. So in these kind of models, you assume there's enough males to sort of impregnate females, and you only model the females themselves. And so in other words, the P, if you added up all the entries, that's going to be half the total population because it's only going to be the females. Anyway, just kind of a little note there. So anyway, we've got the birth rates in the first row, and so you can see there's an entry in each spot. Some of the early ones, if these are like baby classes, they'll oftentimes be 0. And then as you increase towards adulthood, they get higher. And then usually some of the older classes are also 0, right? So usually some aged females stop giving birth. And then the S's are the survival rates. And so each one of these rows, the rest of the rows, are the survival rates for each class. And so this is like the survival rate of the first class, second class, there'd be all this way down to the last class. And we'll talk about why there's 2 entries in the last row. But let's think about what happens when we do this matrix multiplication, right? So P of t plus 1 equals A of P of t times P of t. And so here's A. Let's multiply this by the column vector P of t, P sub t. So I'm going to make a hypothetical column vector P sub t. And it has the entries P1, P2, P3, all the way down to Pn, we know, the individual populations in each subclass. And this is obviously a matrix times a vector. And so we basically take each one of these entries and we scale the columns and add them together, right? And so when we do this matrix multiplication, it ends up equaling this. P1 will multiply F1, so P1 F1, and then we do plus, and then P2 will multiply F2. Oops, this would be a 1 right there. And then all the way up to the last ones, right? So Pn Fn. And then below the first row, there's mostly zeros, right? And so it just really ends up being like P1S1 in the second entry. We'll get P2S2 in the third entry, etc., all the way down, dot, dot, dot. And then in the last row, we have 2 things here. So we're going to get Pn minus 1, Sn minus 1, plus Pn_Sn. And so I want to interpret what's going on here. This is our P sub t plus 1 matrix vector right here, right? This is an n by 1 vector. It might look like a matrix, but we're adding things up, and so each one of these things is going to be 1 entry in each spot. So I'm just going to pause 1 second here and let people catch up, and then we're going to interpret what's going on in each one of these classes, right? So we just did one sort of step of the this population model, and let's interpret what's going on in the first row and the second row all the way down to the nth row. So this is the population in the next age class, right? It's the next time step. And so this is the first entry, and so this is like the babies. And so you can see the babies are obtained by birthing from each age class. In other words, when you do like P1F1, that's the population in age class 1, and you multiplied it by their birth rate. And so that's going to be like a fraction. And so P1F1 is going to tell you the number of births that age class 1 gave. P2F2 is the number of births from age class 2. Right? PNFN is the number of births from age class N. And so this first entry right here, I'm going to write down maybe right here, this first row, first column or first row in the PT plus 1 are the births from each class, and they're put into class number 1. Right? That's why they're in the first entry, and it's the births from each class. Let's talk about the rows in between before the last row. So let's talk about the second through the n-1 row. These are just surviving people, right? So P1S1 is the number of surviving population from age class 1. But notice that it's in age class 2. So if you want to be in age class 2 in the next time step, you need to survive from the previous class. Right? If you want to be in age class 3, you need to survive from class 2. And so what these ones are doing, it's saying the age in time t plus 1 equals survival from the previous age class. That's what's going on in those intermediate rows. And then in the last row, this very last row, right, there's 2 entries. And so this is the oldest class. And so if you want to be in the oldest class, you either survived from the previous class or you were already in that class and you survived. And so that's why there's 2 in the oldest class, because they have nowhere to go, right? So once you get to the oldest age, you just survive there until you die. And so this last class consists of people who move up from the previous class and then those who are already there and survived. And so I'm just going to make that last note right down here at the bottom. I'm going to maybe start right here and then do it around. So the oldest age class equals survival from the previous class plus survival from the last class. So I'll call that the nth class. So that's why there's 2 survival entries in the last row of the A matrix, because we want 2 contributions to the oldest class. And so that's sort of how it works. And if you want to just keep stepping along, you just keep doing this matrix multiplication, right? So this would give you the next population value. You multiply it by the matrix again, and it just projects it forward to the next time step. And so we're going to look at a specific example on the next page of that. We'll project the population forward a little bit, and then we'll talk about how eigenvalues and eigenvectors come into play here as well. Again, very useful actual real-world modeling goes on with this type of model. Again, check my website if you want to see an example of that. I'd be happy to send you the paper. So here's a specific example. I've been meaning to actually maybe update this one with my own example, but I haven't done that yet. Anyway, this is another real-world example that I got from a textbook that cites a specific paper. So if you're interested in this paper, I'd be happy to send it to you too. But this one is a model for American bison. And this particular model breaks bison up into 3 classes: calves, less than 1 year; yearlings, which are 1 to 2 years old; and then adults, which are bigger than 2. And so each age class is 1 year. Only adults give birth, which is a very common thing, and each adult female births 0.42 calves. And then we're being told the survival rate of each population. So calves, yearling, and adults have survival rates 0.6, 0.75, 0.95. And then we're given an initial population of 100 adult females. Let's figure out how many, let's determine the herd structure in the next 5 years. And so this is the answer right here, right? So this is the answer to our question is in this table, right? So it says like we have 100 adult females to start, so 100 adult females, none of the other in year 0. And then this is saying in year 1, 2, 3, 4, 5, this is how the population breaks down. And so we're going to recreate this table using our matrix model. So let's write down the information we have. So we have 3 age classes, 1, 2, 3. And so that means we're going to use a 3 by 3 matrix for A. And when we think about the matrix A, right, it has survival rates and birth rates in there. So S obviously stands for survival. The reason that they use F for birth rate is because it technically stands for fecundity. That's like the biological word for birth rate. And so we need birth rates and survival rates, and we're being told those things. And so we're being told that the birth rate of adult females is 0.42, but the other ones don't give birth. And so the class 1 and class 2 don't give birth, so they equal 0, but the adults give birth at 0.42 calves per year. And so that's going to be the first row of our matrix. And then the survival rates we're being told is 0.6, 0.75, and 0.9. So S1 is 0.6, S2, 0.75, and S3, 0.95. So as a bison get older, they're more likely to survive, which is a typical thing in animals in general. Usually the youngest die at the highest rate. And then we're being told the initial age structure. So we're being told there's 100 adult females, and that's it. And so that means our P0 vector, our initial values, are 0, 0, 100. All right, so that's the initial number of calves. That's the initial number of yearlings. So neither of them, we're only starting with the initial number of adults, which is 100. Okay, so let's set up our matrix and do a little bit of matrix multiplication. And so our matrix A, let me just remind you of the form one more time. We do the fecundities across the top row, and then we do the survivals down one across sort of this sub-diagonal, and then you do the last two in the bottom row. But we're only going to have a 3 by 3, so it's not going to be nearly as big of a looking at the matrix, right? So let me do it like this. So A is this matrix then. 0, 0, 0.42, because only adults give birth. 0.6, 0, 0, 0, 0.75, 0.95. And we are going to use the recurrence relationship, the population at the next time step equals the matrix A times the population at the previous time step. All right, so we're going to use this to project the population forward. And so we won't, this is showing the first 5 years in this table. We won't do 5 years. Let's do the first couple years and see that we're going to get that. Okay, so let's do that. Excuse me. Okay, so when we plug in t equals 0 into this recurrence relationship, so at t equals 0, the relationship is the population at time 1. Sorry about that, just meant to write a 1 there. If I plug a 0 in there, that becomes a 1, equals A times P0. And we have all that information. Right? A is our matrix, 0, 0, 0.42, 0.6, 0, 0, 0.75, 0.95. And then P0 was the matrix 0, or the vector 0, 0, 100. So there I did it, right? This is A times P0. And you can just do that matrix multiplication, and you get the next time step, right? We'll get our P1 vector by doing that multiplication. So when you do the multiplication, you get 42 in the first spot, you get 0 in the second spot, and you get 95 in the third spot. And so let's analyze what just happened here. Right? You had only 100 adults, and so 0.42 of them gave birth, and so that resulted in 42 births. And so this is 42 births in the first time step. There's 0 in the yearling class because there were no calves to move up to yearlings, right? And so you had no one to move up. That's why this one stayed as 0. So there were no calves to survive to become yearlings, but it will in the next time step. Now we have calves, and so in the next time step we'll have some yearlings. And then 95% of the adults should have survived. So if we had 100 of them, 95% of that is 95, and so only 5 adults died. And so that's how we can kind of think about that first time step. Let's just do one more, and you can see this is what it says in the first, right? In year 1, there should be 42 calves, 0 yearlings, 95 adults. That's exactly what we got. Great. Let's just show that we also get for t equals 2, and then we'll move on here. And so, let me do another color here. If we did t equals 1, so plug a t equals 1 in here, we get P2 equals AP1. And this is P1, right? And so we're going to multiply our matrix A times P1 now. So 42, 0, 95. So we're just going to project it forward. I'm just doing A times P1. And when we do that matrix multiplication, we get the following. 40, 25, 90. And so that's our P2 vector. And so we had some calves move up to yearlings, so now we have something in each class. And you can see this is what it says in the table, right? 40, 25, 90, that's exactly what we got. And if we kept going with this, if we did the matrix multiplication again, we'd get the third row and the fourth row, etc. And this is fine, but let's come up with the closed form solution. And so let's do the same thing we just did a second ago with the bacteria. Remember with the bacteria, we came up with this closed form solution, and it looks very similar when we do it here. So notice this. So let's do the same thing. So notice, P1 was A times P0. P2 was A times P1, and we just said P1 was A times P0, and so this equals A times P0, and so we get A times P0, which is A squared P0. If we did P3, we would do A times P2, and P2 is A squared P0. So we get A cubed P0. And so notice that it's the same pattern we just saw with the bacteria, right? When there's a 1 here, there's a 1 here. When there's a 2 here, there's a 2 here. When there's a 3 here, there's a 3 here. And so the general form of this is Pn, the nth population will be A to the n P0. And again, that's super, super nice, because if you want to do the 100th time step or the 50th time step or whatever, you don't need to do 100 time steps. You just need to raise a matrix to a power. And if you did this on a computer, it'd be really, really easy to do. So this is the closed form solution. And it's really nice because if you wanted to do, say, P sub 50, you don't have to do 50 time steps. You just have to raise a matrix to a power, which is something a computer is really good at. Okay. The last thing I want to talk about is where eigenvalues and eigenvectors come in, right? So this has been a nice application of just matrix multiplication so far, but where does the eigenvalue and the eigenvector come in? And so that's the last thing that we just want to look at here, and we'll figure out whether or not this population is growing or declining. So if we just kind of look at the population values here, like the total population in the column here, the population is going up, but is it going to happen forever? What's the rate that it's going up? And so that's another nice thing that eigenvalues and eigenvectors tell us. So let's look at that. So the long-term growth rate and age structure. So let's let lambda star be the eigenvalue of the Leslie matrix with the largest magnitude. So what that means, it's the biggest one, is the one way to think about that. We call that the dominant eigenvalue. It dominates the other ones, right? The biggest. Well, it turns out that that eigenvalue tells you whether or not the population is growing or not long-term. It tells you the long-term growth rate. And so here's how it works, right here. If the long-term growth rate is bigger than 1, the population is going to grow. If the long-term growth rate is less than 1, the population will decline. And if it equals 1, it oscillates. Again, very similar to this thing we just saw with the bacteria, right? We saw that this bacteria was doubling every time because the growth rate was bigger than 1. And so we have a very similar thing here where we have a long-term growth rate that if it's bigger than 1, it means the population is growing. If it's less than 1, it's declining. Here's why it works. So there's kind of a key thing in the assumption here, which is that suppose the population reaches a stable age distribution. That's the key thing that we're assuming. So it's not like immediately right when the population starts, but it's like way down the line, we reach a stable age distribution. What that means is the population might change each time step, but the proportion in each class will not. And so what that means is this. We have this relationship. This means that at the next time step, it's going to be the same percentage in each class, just some growth or decline of each class. Right, so this is the stable age distribution assumption. The stable age distribution has been reached. Well, we also know this. This is just the definition of the Leslie matrix. That's just the definition of the model. Pt plus 1 equals AP of t. And so we have two expressions for P of t plus 1, right? And so that means we can set these two things equal to each other, and so lambda P of t equals AP of t. And this is the definition of an eigenvalue eigenvector. Right? We have two expressions for P of t plus 1, so we can set them equal to each other, and that becomes the definition of an eigenvalue eigenvector, right? And so it turns out that the dominant eigenvalue tells you the growth rate, and then the thing I skipped up here is that the dominant eigenvector that corresponds to that will tell you how the population is distributed. And so let's look at the example from the previous page. So I'm not going to do the work here, but let me just show you the dominant eigenvalue and vector from this matrix here. So work not shown, but from the previous page, the lambda star, which is the dominant eigenvalue. I used a computer and did this, so I didn't even do it by hand, is 1.10. And so that's the biggest one. And that's bigger than 1. And so this is telling us that the population on the last page is growing by 10% each time step. After the stable age distribution is reached. So not right away, but after you run the model for enough time and it has enough time to sort of settle down into a stable age distribution, then it's going to grow 10% every time step. In other words, if we look back at these percentages here, right, it went up 37 the first time, that's not 10%, and then it went up, 18 the second time step, that's also not 10%. So it's going to oscillate a little bit at first, but if you ran this for long enough time, usually it doesn't take that much time, maybe 10 years or something like that, eventually it would be going up by 10% every time step. So it needs a little bit of time to reach that point, but it'll eventually get there. And then, when you find the eigenvector associated with this, it tells you how the population is distributed. And so again, I did this on a computer. This is the kind of thing that you learn how to do on computers in upper level classes. Like I teach how to do it in modeling classes or in methods of applied math or something like that, which is Math 3500. We learn how to do this stuff on a computer. And so the eigenvector tells us the age structure. And so for lambda equals 1.10, the eigenvector turned out to be 0.24, 0.13, 0.63. And I had to normalize it to make it so that those numbers added to 1. I mentioned that you can multiply any eigenvector by a scalar and it stays an eigenvector. But you could just basically add the numbers up and divide by the total. And then this tells you that there's going to, long term, there's going to be 24% of the population in class 1, so calves. 13% are going to be yearlings. And long term, 63% will be adults. And so that's very useful, right? Like, because you know that most of the population are going to be adults, right? There's going to be the smallest percentage in the middle class. And so, just for example, if there's some disease that hits adults specifically hard, for example, well, that's going to hit this population really hard because most of the population is adults. Anyway, you can learn lots of things sort of long term about the population from these things, but it's a really nice application of eigenvalues and eigenvectors, again, that really do have real world applications, and I'd love to share with you my project if you wanted to talk about that sometime.